Hello and welcome to a video. This one's going through Phoebe's question, which she gave me in the lesson recently. If you're not in my class, then I'll just quickly give you a quick introduction to the question. Okay, so this is one of those really difficult de Moivres questions where we've already proved this, and I won't go through how to prove that result because it's well established in the textbook. There's a technique, once again, using de Moivres to establish this result. Now, so I'm not going to go through how to establish this result again. It was really the bit after the question where it said, hence show that cosec squared pi over 7 plus cosec squared 2 pi over 7 plus cosec squared 3 pi over 7 does in fact equal 8. And you can check that on a calculator as I did, just to see that it is true. It's quite an amazing result. You're like, oh wow, you know, that's a lovely result. Well, we're going to prove it using the fact that this identity, sorry, let me just give it a third line for the equals, using the fact that this identity is true. Now, yeah, this is a good question. It's a really tough one. This is the way I ended up doing it in the end, and I don't think it's the same way as is shown on the Mad as Maths website, which is where we got the question from, which is a great website, by the way, for finding really, really difficult questions. And by the way, can I just commend my 13 doubles on finding some absolutely really tough questions, which totally made me fumble in class the other day. Yeah, what can I say? I was not very good. Okay, so here's how we do this. I would say, okay, sine 7 theta is sine theta times by this altogether. So I'm just, you know, taking out a factor of sine theta, which seems like the obvious first move. Now, what I did do wrong in class was I got obsessed with this idea that I can do something with a slight modification to this polynomial. Because it looks like it almost factorizes, but like, you know, when sine theta is 1, but you're left with a remainder of 1, so I made this into an 8. That is definitely not the way to go here. The way to go is to just, because, I mean, the hint you're given is the fact that it's pi over 7, 2 pi over 3 pi over 7. You're going to get that when sine 7 theta equals 0. So let sine 7 theta equal 0. And the problem with my strategy was it ended up with like a 1 here or a minus 1 here, which means that needs to be 1 or minus 1 as well, which means that needs to be 1 or minus 1 as well. And then you don't get pi over 7, 2 pi over 7 and 3 pi over 7 dropping out. So it was a stupid idea. So apologies for that. Okay, but let sine 7 theta equal 0. Then 7 theta is 0, pi, 2 pi, etc. And so theta is 0, pi over 7, 2 pi over 7. And we'll go all the way up to, because I just want to talk about some of these solutions, we'll go all the way up to pi, 5 pi over 7, 6 pi over 7. Well, we've got 7 solutions there, haven't we, yeah? Now, the sine theta equals 0 solution corresponds to that one, 0, yeah? So the 6 solutions coming out of this polynomial order 6 must be these solutions, here, 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 and here, and here, yeah? Now, some of those solutions are repeated, because sine of pi over 7, it's worth pointing out, is exactly the same as sine of 6 pi over 7. And sine of 2 pi over 7 is the same as sine of 5 pi over 7. And if you want to know why that is, it's simply the rule of thumb for sine, as I call it, which is that sine of pi minus x is exactly the same as sine x. That's why when we're solving for sine, in degrees anyway, we do 180 minus first answer to find your second answer, or you use cast and you do something similar, but it really comes from, you know, cast diagram and the symmetry of the sine graph. So, you know, what we've got here is that one matches with that one matches with that one matches with that one, which is interesting, yeah? In other words, this cubic, if you like, has repeated roots. That's what we're seeing here. Now, if we let sine squared theta equal u, then we can rewrite that polynomial as 7 minus 56u squared plus 56u plus 112u squared minus 64u cubed, yeah? And that's nice, yeah? Now, we know the roots for this equation, don't we? We know that sine squared pi over 7 sine squared 2 pi over 7 and sine squared 3 pi over 7 solve this equation. Well, that's lovely, isn't it? We know that they solved that equation because they solve sine 7 theta equals 0. So if they give you the roots for that, they must give you the roots for where this equals 0. We've already excluded the 0 root because that goes with a sine theta. And these 6 roots must go with this. We've already discussed the fact that this one's the same as this one, this one's the same as this one, this one's the same as this one. So we have in fact got 3 repeated roots, and so we know these 3 repeated roots here. Yeah. Now it's a shame that it didn't ask us to sum sine squared pi over 7 plus sine squared 2 pi over 7 plus sine squared 3 pi over 7, because note, yeah, that we could easily find now that sine squared pi over 7 plus sine squared 2 pi over 7, yeah, and this is my immediate thought. I wish this was the question, if you like, because I could easily find the answer to that, because the sum of the roots of a cubic, what are the sum of the roots of a cubic equal? Well, they equal minus b over a. Yeah. Now, what's your minus b over a in this equation? Well, your minus b is minus 112, and your a is minus 64. Yeah. I don't know what that cancels down to. I'm going to have to do it in my head. Oh, this is where it goes wrong. 56 over 32, 28 over 16, 14 over 8. This is such a bad way of doing it. 7 over 4. So I haven't got my calculator handy, but like I will check it after the video. I reckon if you do that squared plus that squared plus that squared, it will always equal 7/4, which is an amazing result in itself. Just a shame it's not the result we're trying to prove, yeah? Oh, damn. But I've got a trick, yeah? We can do a substitution, yeah? Let W equal 1 over U, yeah? And this should remind you of those substitutions you occasionally make in the questions which are about the sum and the roots of polynomial equations, yeah? Because if I perform this little substitution, what do I get? I get 7 minus 56, and because that means U is 1 over W, yeah? So 56 times 1 over W plus 112 times 1 over W all squared minus 64 times 1 over W all cubed, yeah? And that looks a little bit nasty, but let's just times through by W cubed, yeah? And we get 7W cubed minus 56W squared plus 112W minus 64 equals 0. Now, why have I done this? Well, because these roots are reciprocal of our old roots. So this is going to have roots of cosec squared pi over 7, cosec squared 2 pi over 7, and cosec squared 3 pi over 7. And I can use exactly the same trick as I've done up there. I can now just simply say, so this has roots cosec squared pi over 7, cosec squared 2 pi over 7, and cosec squared 3 pi over 7. And so what can I say about the sum of these roots? Well, it's minus b over a. Minus 56 divided by 7 is 8. I'm particularly proud of this proof. I've had a little think about it. It's always easier once you sort of like get home and you can do it calmly in you know, in calm conditions. Although actually, having said that, I had my kids around me and that meant that it wasn't that calm. So that should equal the minus b over a for this cubic equation, and that equals minus 56 over 7, which is of course 8, yeah? Hence the result is established. Okay, I hope you enjoyed that, and I hope you see what I'm getting at here. That would be a very difficult question if it came up in the exam. I think they're more likely to ask you this line: prove that sine squared pi over 7 plus sine squared 2 pi over 7 plus sine squared 3 pi over 7 is 7 over 4, because then you haven't got to do that little trick at the end with the substitution. But it's a good question. It's a really interesting question. It's an exciting question. Thank you for the question, Phoebe. All of my class who are watching this video, keep finding me these really difficult questions, especially if I get it wrong in class. I'll definitely buy some kind of a cake for a mistake or something like that. Okay, thanks for listening. Bye-bye.